But I've chosen one other topic to talk about that combines graph theory with some very, very simple, even almost silly, but important example to do with codes. So let me finish with that. So let's go back to the paperwork, see if I can explain this. So we'll be seeing lots and lots of examples of graphs. And here's a very simple graph that, of course, I'm a geometer, so it's natural for me to take geometrical objects and there's a succession of graphs that are coming from the so-called Platonic solids. Possibly the easiest to understand is the cube. So the cube obviously is one of the 5 Platonic solids. Here it's drawn in the usual sort of way. And the graph associated to this 3-dimensional object is just, you forget the fact it's solid. You just look at the configuration of vertices and edges on the cube. So this is, you might call it, what you get is the cube graph. And it's important to see that here we have edges, because I've sort of drawn it as if I'm sort of looking at it in the usual way. Edges cross here. If I had to take a photograph and it was transparent, you'd see edges crossing, but where they cross here, that's not a vertex. The vertices are the big blobs. So of course the cube graph has 8 vertices. And at each vertex, there are 3 edges coming in. So we say the valency, or the degree is the mathematical word used, the degree of each vertex. All the vertices have degree 3. All of degree 3. It's what's called a regular graph, because all the vertices are of the same degree. And of course, there are 12 edges. And one can do a check here, because if you take from each vertex, there are 3 edges. So you multiply 8 by 3, but each edge contributes to 2 vertices. So there should be, we sort of got 24 edges, but each edge has 2 ends. So you divide by 2 and that gives you 12. So that's the number of edges, that's correct. Normally it's more complicated because the degrees are not typically a graph. In a graph, the number of edges meeting at each vertex is not the same number. Here it is. Now, if we sort of think more abstractly, we can actually get rid of these unauthorized crossings by just sort of pretending we're looking at the cube through a face, through the front face. So we could also draw the cube graph like this. It looks rather different, but the point about graph theory, it is the same graph, or if you like, say the graphs are isomorphic. It's obviously the same configuration of vertices and edges. Often it's not so obvious that you have the same graph. But here I could easily label the vertices in such a way that everything corresponds. If you do that, it's clear that these graphs are really the same. But the fact that I've now done it in such a way that none of the edges meet except in a vertex means this is an example of what's like all the other Platonic graphs. This is what's called a planar graph. The fact that it can be drawn, it doesn't have to be drawn, but it can be drawn in the plane so that there are no unauthorized crossings of edges. It's an example of a planar graph. So it's an important property. Well, as I say, that's true. There are also what are the other Platonic solids? There's the tetrahedron. Incidentally, the tetrahedron graph, you can draw it in here. 2 ways of drawing the graph from the tetrahedron. It's certainly a planar graph. There's a version of it drawn in the plane. But it can also be drawn as a square with the 2 diagonals. You just have to understand that where the diagonals cross, that's not a vertex. These look very different, these pictures, but they're really representing the same graph, or what are called isomorphic graphs. And this is the tetrahedron graph, tetrahedral graph. It's also an example of what's called K4. It's the complete graph on 4 vertices, because we take 4 vertices and there's an edge joining any pair of vertices. So there's another example of a graph. But let's go back to the cube. I got a bit distracted there. Another property of the cube graph, it's also what's called bipartite. I want to explain this concept. And that means that you can actually color the vertices with just 2 colors, so that there's no vertices, no 2 vertices with the same color are adjacent. So if I call my colors alpha and beta, you see I could take, almost done it with the numbers actually. So if I call this vertex, if I color that alpha, so alpha represents a color, and I don't want the same color on adjacent vertices, so I have to color these 3 vertices beta, because they're adjacent to alpha, they're joined to alpha by an edge. And then I have to make sure that this vertex is alpha, colored alpha, this vertex, which was number 8, is colored alpha. And we've got 2 alphas, this has to be a beta, and then we can finish by coloring this vertex alpha. So in this way, I've assigned either alpha or beta to each vertex, and there's no edge joining the same 2 Greek letters. So it's what's called 2-colorable, this graph. The vertices can be colored in such, just with 2 colors. Normally it's not possible. You need more than 2 colors, so that no 2 adjacent vertices have the same color. And that means that also gives another way to draw the graph. For bipartite graphs, you tend to put all the vertices with 1 color on the left and all the vertices with another color on the right. So you could actually represent the cube graph in this way. And you see each vertex on the left is joined to 3 vertices on the right. So maybe it's not joined to the corresponding one opposite it. So you've got edges like this. It's going to look a bit of a mess, but got to get 12 edges in all. Just leave out the one opposite it. So there's another representation of the cube graph that emphasizes the fact that it's bipartite, because we've actually partitioned the vertices into 2 subsets, and no 2 vertices in either subset are joined by an edge. The edges only go across from one subset to another. That's the concept of being bipartite. Okay, so those are very simple examples of graphs. We'll be looking at rather more sophisticated examples. We'll be trying to understand, for example, how you can work out, if you see a messy graph, it could be planar. There could be a way of sort of rearranging the edges, as we did for the cube, to make it a planar graph. But it's often not obvious to understand whether or not that's possible, or to prove that it's not possible. And that's one of the concepts we'll be looking at. And we'll also see an algorithm for this coloring of a graph, coloring the vertices of a graph, using the least possible, or trying to use the least possible numbers of colors. That's related to the so-called chromatic number. It's an important invariant of a graph, with applications, I should say, even to timetabling modules. That is, if students are present on campus. So let me just finish off this example, because I want to relate this graph, this cube graph, to give a very naive introduction to linear codes, binary linear codes. So what I want to do here is I want to keep this cube configuration here, but I want to give you a 4th way. We've seen 3 ways, already 3 pictures of representing the cube graph. I'm going to give you a 4th way, a more combinatorial. So a 4th representation of the cube graph. And for this, I'm going to think of the origin of the cube. I'm going to think of the cube as placed in Cartesian space, with origin at vertex number 8. So the axis, we've got the x-axis down here, the y-axis and the z-axis up top, and then we can just write down suppose that the length is 1, we can write down the Cartesian coordinates of the vertices. I'm not going to use brackets or commas, I'm just going to write them in a row. So the origin would be 0, 0, 0. Then we might have 1, 0, 1, that would be this point here, labeled 4. 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, and finally 1, 1, 1, which corresponds to vertex number 2. So that's a way of encoding really the 8 vertices representing the 8 vertices of the cube. Incidentally, of course, that explains why there are 8 vertices, because it's really 2 to the power 3. Now you can write down the vertices of a 4-dimensional cube without difficulty and realize there must be 16 of them. But anyway, what I want to say here is I really want to think of these as words. Think of them, they're not quite arranged in dictionary order, but you can think of this as a sort of alphabet with 2 to the 3 words, because with the letters being 0 and 1. So think of these as words with the letters being 0 or 1. And I'm going to distinguish 2 of these words. I'm going to distinguish the origin and the vertex furthest away, which I finished with coordinates 1, 1, 1. And these are going to be special words. They're going to be called code words. So we're just going to have 2 code words in this very simple example. And the idea is this. I think we can get rid of the picture of the cube now. So supposing I want to transmit a message with just 1 character. So supposing I want to transmit one of 2 messages. So either no or yes. And if I want to transmit no, that corresponds to sending 0 electronically. If I want to say yes, that corresponds to sending 1. And this could be a very important message, it could be a signaling system for a train or something where we can't really make any mistakes. So the problem is, if we're sort of doing this through some cable or something, there may be an error, and it's maybe with 10% possibility, or maybe 1%, I don't know, the numbers may get muddled up. So to try and avoid that, you send more information than you need in the mathematical sense. So if we want to actually send the message no, what we do is transmit not just 0, but 3 zeros. It's what's called a repeat code. I mean, it's a very silly idea, but it actually illustrates the much more complicated theory we'll be talking about in the module. So this is really a repeat code. Just repeat the number twice more, so 3 times altogether. And if we want to say yes, we don't send a single one, we send 3 ones. So in other words, we use one of these code words to send our important no or yes message. And why do I need 3, say not 2? Well, the point about 3 is that even if one of the characters is changed, is corrupted, we can understand what the original message was. So this code, this is a repeat code, and it does what's called it corrects one error. In the sense that if we receive, instead of 0, 0, if the signal box receives, say, 0, 1, 0, the idea is that there's no message that corresponds to 0, 1, 0, but if there was just one error, we can say really what this means is 0, 0, 0, so it must be a no. The message must have been no. So you see, I mean, if there was a 10% chance of error, the chance of 2 errors would be 1%. So the idea is this is a pretty certain way of getting the right message. But mathematically, what's going on is that we're finding 2 code words amongst our list of 8 words that are so that each word is within a distance of one of the code words. You see, if we're not actually a code word, these three words correspond to this message because they're really just a distance one apart. There's just one error to get back to there. And these three words, you just change a 0 to a 1 and you get back to this message. So any word is a distance, if you like, what's called Hamming distance, at most 1 from a code word. Or you can, perhaps I shouldn't have removed the picture of the queue, which I've now lost, because in fact you can see that pictorially, because this origin here is one code word, and these three with a square around, these will be the words closest to that message. This was the no message, and the yes message corresponds to this vertex, and that will be closest to these three words. So if you like, the set of words has been sort of split up. And that idea is, we'll be explaining that in a much more sophisticated setting using linear algebra modulo 2 to understand much bigger sets of words like 120, 5112 words, and trying to find subsets of them which allow us to transmit messages and be able to correct one or more errors. Okay, well, I hope that gives you an introduction to the course. I will be putting, of course, it's a semester 2 course. Should have said that at the beginning. I will be putting during September some more material on the Keats pages so that you have a clearer idea of what's involved in the course. Some of the material may be from last year, but nonetheless, it will give you an idea. Don't print anything out, but you'd be welcome to sort of look at it online. Okay, I hope to see you in person sometime in the second semester. Thank you.